Everyone, after having looked at the difference of squares and a perfect square scenario for factoring, now we're going to focus on higher power, which is cube. So for cubes, we have two different identities. One is for the sum of cubes and one is for the difference of cubes. The sum of cube can be factored as a plus b and then an a squared minus ab plus b squared, whereas the difference of cube is a minus b a squared plus ab plus b squared. Okay, so the difference a squared b, yeah, the difference comes about from in where this negative is. Okay, so now here again you need to know some cubes of some of the numbers. So like 1 cube is always 1, 2 cube is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. I believe it is sufficient to know up to 5. Numbers beyond 5 is alright, so these you don't need, but these are some numbers that you should be aware of, so that if you see them somewhere, then it should click that, oh wait a second, it's probably difference of cubes or sum of cubes. I mean, also the fact that one of the variable will have a cubic power should be sufficient to denote that. So for example here, that is x cubed plus 5 cubed, so which comes out to x plus 5 and then x squared minus x times 5 plus 5 squared, which then becomes x plus 5 x squared minus 5x plus b squared. Oh, 5 squared is 25. So again, knowing some of the basic squares and cubes is always a nice thing. Now the second example, slightly not direct. So you have x to the 6 and you have a y cubed. So this cube signifies that it's probably a difference of cubes, right? So 64 from our list is 4 cubed, so this is 4y cubed. And x to the 6 can be written as x squared cubed. Okay, now what's going on here? What's going on here, here's an aside. When you have x to the power m to the power n, then these become product of powers, right? Because x squared cubed is actually means x squared times x squared times x squared 3 times, which becomes 2 plus 2 plus 2, which becomes 2 times 3, which becomes 6. So once you've written it in that form, this is now a sum of cubes. And the sum of cubes becomes an x squared plus a 4y. And you have an x squared squared minus x squared times 4y plus a 4y squared. Okay, which comes out to x squared plus 4y. X squared squared is x to the 4. Then you have 4x squared y and then 16y squared. So there is a little bit of work before you apply the sum of cube. And the work arises from having to rewrite x to the power 6 as x squared whole cubed. Alright, let's look at one last example. So here again, we're going to use the fact that 1 cubed is also 1. And further, that x cubed y cubed can be written as x times y cubed. Why does that work? It's because here xy cubed, what does that really mean? It means xy multiplied with xy multiplied with xy, which further means that I can collect these x's to get x cubed, and I can collect these y's to get y cubed. And in the same way, 27 is 3 cubed. So this is 3 cubed minus 3xy whole cubed. And now I apply 1 minus 3xy, 1 squared plus 1 times 3xy plus 3xy squared, which comes out to 1 minus 3xy, 1 plus 3xy plus 9x squared y squared. So these are 3 examples. One, the plain simple application. Second, sometimes you may have to think about how to write a higher exponent as a cube, like x to the 6 can be written as x squared cubed. And lastly, the regular trick as with squares, that 1 cubed is 1, so you can always apply this difference in sum of cubes for terms that have just 1. And as well as things that look like x cubed y cubed can also be written as a cube of xy. Now that brings us almost towards the end of factoring discussions. So I'm going to end this video here, and then in the next video we're going to look at, because we've learned all these different methods for factoring, we'll go through a general strategy for how to think about when you see a factoring problem, what steps to follow, what observations to make, what patterns to see. That's going to be covered in another video where we look at factoring strategies. Thank you.